Have you ever thought about the dynamic array or array list? It's probably the data structure you use most. We're always told that adding an element is super fast, O of 1, constant time. But we also know that every now and then it has to resize, copying the entire array over. And that's O of n, which is incredibly slow. So which one is it? Is it fast or is it slow? The answer, it turns out, is both. And understanding why is going to change how you look at code.
This right here, this is the paradox we're going to unravel. It seems impossible, right? But the answer lies in this really powerful idea called amortized analysis. It's the lens that lets us see the true, practical performance of data structures even when they have these occasional, super expensive operations.
So you see it laid out like this. On one side, the worst-case cost for a single append is O of n. I mean, that looks terrible. It suggests your program could just grind to a halt. But on the other side, we're promised this beautiful amortized cost of O of 1, which is as fast as you can get. This isn't some kind of trick, it's just a much more realistic way of measuring performance over time.
So let's dive into what I'm calling the array list paradox. Cracking this is the key to understanding why so many of the tools we rely on every day are so incredibly efficient, even with these scary worst-case scenarios hiding in the background.
Here's a really simple way to think about it. Imagine you've got a coffee subscription that costs you $30 a month. That one-time payment feels kind of big, but if you spread that cost out over the entire month, the amortized cost of your coffee is just $1 a day. We're about to apply that exact same thinking to our data structure.
All right, enough with the analogies. Let's actually count the true cost. To really solve this paradox, we have to stop looking at operations in isolation and start looking at the total work over a whole sequence of appends.
Okay, so let's trace this out. We start with an empty array. The first append? Easy. Costs 1 unit. Now, for append number 2, the array is full. We have to double the capacity to 2, copy that one element over, and then add the new one. That's a total cost of 2. For the third append, whoops, we're full again. We have to double the capacity to 4, copy 2 elements, and add the new one, costing us 3 units. But then look, the fourth append is cheap again, back to a cost of just 1.
And as we keep going, a really clear pattern starts to emerge. These expensive operations, the ones where we have to copy everything, they only happen when the size of the array hits a power of 2. So append number 5 costs us 5 units of work. But then appends 6, 7, and 8 are all super cheap. Append 9 is our next expensive one. The key thing to notice is that the stretches of cheap operations get longer and longer each time.
Okay, let's add this all up. The easy part first. No matter what, for n append operations, we have to do n simple additions. That's our baseline cost right there.
Now for the tricky part, all that copying. The number of elements we copy follows this geometric series. 1, then 2, then 4, then 8, and so on. Now that looks kind of scary, right? But here's the magic of this particular series. The sum of all those copies always adds up to be less than the total number of elements. So for n appends, the total number of copy operations is roughly n. So you put it all together, we've got n units of work for the actual appends, plus about n units of work for all the copying combined. That means the total work for n operations is in the ballpark of 2n, which in big O notation is just On.
And that brings us right to the formal definition of amortized cost. It's simple. You take the total cost for that whole sequence of operations, which we just figured out is O of n, and you just divide it by the number of operations, n. That gives you the average cost per operation.
And there it is, the big aha moment. When you take the total work, O of n, and you divide it by n operations, you get a constant, O of 1. This is the proof. This shows that, averaged out over a sequence, the cost of adding an element to a dynamic array is constant time. The paradox is solved.
Now, what we just did there is called the aggregate method. It's probably the most intuitive way to understand this, but it's worth knowing that computer scientists have a few different ways to prove this, and each one gives you a slightly different way of thinking about the problem.
So, we just use the aggregate method. Add everything up and divide. Simple. Then there's the accounting method, which is like prepaying for future trouble. And finally, the potential method, which is a more formal mathematical way to do the same thing using something that acts like potential energy. All three methods get you to the same O of 1 result. They just take different paths.
Let's look at that accounting method, because it's pretty clever. Think of it like this. For every single append, you charge a flat fee of, say, $3. $1 pays for the actual append operation right now. The other $2, you stash them away in a bank account. You just keep saving. Then, when a big, expensive resize comes along, you use all that credit you've saved up in the bank to pay for it. The proof just shows that your bank balance will never go negative.
Okay, that's the theory. But why should you actually care about this? Well, this isn't just some academic puzzle. This principle is the silent workhorse behind the software and tools you use every single day.
For starters, if you're ever in a coding interview, I can almost guarantee you'll see questions just like these. Being able to explain not just that array list append is O of 1 amortized, but why it is, shows a much deeper level of understanding, especially if you can explain what would go wrong if you didn't double the capacity. And it's not just for interviews. You're using this concept constantly. Java's array list, Python's list, C++'s vector, they all rely on this exact geometric growth strategy to give you that blazing fast O1 append. It's also the secret behind why hash tables can resize themselves efficiently.
And this really highlights how much that growth strategy matters. We've seen that doubling gives us an amortized cost of O1, but what if instead of doubling, we just added one new slot every time we ran out of space? What happens? Well, your performance just completely falls off a cliff. The total work balloons to ON squared, making the amortized cost ON. It's a disaster. That multiplicative growth factor is everything.
All right, there's one last really crucial thing we need to clear up, because this trips up a lot of people. The terms amortized and average case sound similar, but they mean very different things.
See, average case analysis is all about probability. It's basically making a bet that your input data will be random and not malicious. Amortized analysis doesn't bet on anything. It looks at a worst-case sequence of operations and gives you a rock-solid guarantee on the average cost for that specific, worst possible sequence. It's not a probability. It's a hard limit on the total work you'll have to do.
In this whole idea, it's not some new fad. It was formalized way back in 1985 by the brilliant computer scientist Robert Targent. This work completely revolutionized how we analyze algorithms because it gave us the mathematical tools to prove that data structures that looked slow on paper were actually incredibly fast in the real world.
Okay, so let's boil this all down. What are the big takeaways? First, amortized analysis is all about averaging cost over a sequence. Second, it proves that having a few very expensive operations is totally fine as long as they're paid for by many cheap ones. Third, remember it's a worst-case guarantee, not a probabilistic guess. And finally, for dynamic arrays, that doubling strategy is the secret sauce that makes it all work.
So I'll leave you with this question. Now that you have this new mental model, this idea of amortizing cost over time, what other operations that we think of as slow might actually turn out to be incredibly efficient when you zoom out and look at the bigger picture?